Hello and welcome. In this lecture, we're going to introduce the mathematical idea of a discrete time signal and talk about some quick examples. The purpose of the channel is education for all, with the objective to study less but smart. The channel offers subjects in the pathways of communication systems, signal processing, control systems, AI, and IT. If these courses are of interest to you, please subscribe and share with your colleagues, friends and class fellows. Typically, signal processing has been a part of the electrical and computer engineering curriculum. However, over the past few decades, the ideas of signal processing have been expanded to areas of applied mathematics, statistics, computer science, geophysics, and many other application disciplines. So it's really a very important field as far as technology progress in the world today. Initially, signal processing was effected in an analog fashion. As signals were analog, we processed signals using resistors, capacitors, inductors, and transistor-based analog circuits. But since 1940s and with the invention of the digital computer, signal processing has increasingly become an area that is performed on a digital computer with digitized signals. And now, instead of using resistors, capacitors, inductors, we're using code, right? We're writing programs in a language like Matlab, Python, C, etc. And there's some distinct advantages to thinking and working digitally. First is the fact that digital processing is very stable. The parameters of a signal processing system once they're loaded into computer memory won't change over time, as the components age. And also programmability and reprogrammability. If we'd like to change our system, it's just a matter of changing few lines of the code rather than unsoldering a resistor or capacitor. And as computers have shrunk from taking the size of an entire room to something you can fit inside your pocket, digital signal processing has really become ubiquitous. So just a few of the many different applications of digital signal and digital image processing. An iPhone is a great example. There's tremendous power of speech processing that goes on, for example speech recognition. There is tremendous image processing capabilities in the digital camera that is inside the phone. And then there's a tremendous amount of digital signal processing for communications and networking that allows data to be sent back and forth from the iPhone. The DSP algorithms are designed and analyzed in Matlab, converted into C or C++ and are implemented in a digital signal processor or computer. The processed data is either shared to another computer or digital to analog converter for the desired playback. Just a few other examples include digital cameras, computer modems, security systems like iris recognition, music synthesis, radar, sonar, astronomy, medical imaging, robotic navigation, facial recognition and analytics, cochlear implant, seismic signal processing. The applications of signal processing really are truly vast. The goal of the course is for you to develop intuition about signals, about systems, and really learn how to reason analytically about these systems. There will be some MATLAB programming that will allow you to deal with signals on a first-hand basis. And this allows to process signals and systems and develop a lot of intuition with MATLAB. We're going to learn about signals as living in vector spaces. We're going to bring in the ideas of linear algebra, which are very powerful for thinking about signal processing systems. Then we're going to define and talk about different types of systems. We're going to learn about the all-important convolution operation. In this presentation, we're going to make a quick motivation of the idea of signals and systems in signal processing. Signal processing is the field that deals with signals and the systems that process the signals. If you look up the definition of signal in the dictionary, it will basically say something like that a signal is some physical quantity that carries information. There are lots of examples of signals. We're virtually immersed in them, constantly, throughout our daily lives. 4 quick examples are speech signals that transmit language between people via acoustic waves, radar signals that tell us about where the intended targets are via reflections of electromagnetic waves, electrophysiology signals like electrocardiograms, ECGs, that tell us about information on processes inside our body, like how our heart is operating, and the last example is about financial signals that tell us about events that are going on in the economy. So the important thing to remember is that signals carry information. Systems, on the other hand, manipulate the information that's carried by a signal. A system is generally defined as taking an input signal, one signal, and creating a second output signal. And that output signal somehow has its information manipulated by this system. The study of signals and systems is the area of signal processing. And if you go to the IEEE Signal Processing Society web page, you'll actually see a definition of signal processing. It involves the theory, the mathematics, and the different types of manipulations that we might apply to signals, such as filtering them to remove noise, coding them to improve the ability to compress them or transmit them over a communication channel, estimating physical quantities inside a signal, such as a target in the radar signal. And where the breadth of potential signals is really vast. There's just an incomplete list. We have audio, video, speech, image, communication, etc. and many, many different types of signals. In this course, we're going to learn about signals, and the systems that process signals. Recall that signal processing systems are called on to manipulate the information carried by signals. So the way that we're going to represent and think about signals is that they're mathematical functions. So a signal is a function that maps an independent variable to a dependent variable. Let's meet those variables. We're going to denote a signal typically as a lowercase letter x as a function of a variable n. And we're going to call the signal x of n. And basically, for each value of n, it creates the value x of n. So in this course, we're going to focus on discrete time signals. In a discrete time signal, the independent variable n is an integer number, and typically, we're going to refer to n as the time variable. Even though there are lots of examples of signals that are not a function of time, it's convenient to refer to n as the time variable. And then the dependent variable is going to be either a real or a complex number. So given a particular value of n, the number x of n is either going to be a real or a complex number. And here's a plot of a signal x of n. So for each of the discrete values of n that are integers, for example, n equals 3, the function x of n, or the signal, creates the value x at the time point 3. And it's tradition in signal processing to use square brackets around the time index just to indicate very clearly that this is a discrete time signal. So signals are our functions. We're going to have a lot of opportunity to plot signals, and we're going to plot them as follows. We're basically going to use the vertical axis will be the signal value, the dependent variable. And the horizontal axis will be n, or the time variable. We'll have the opportunity to think both about signals that are finite length, for example, that exist and are defined only for values of n, in this case, between -15 and +15. But we'll also have opportunity to talk about signals that are infinitely long, that go on for all time, all the way from -infinity up to +infinity. And what is clear from context, we will often suppress all of the labels just so that we can see the signal in this more abstract form. So plotting signals, we're going to do it in the following way. It's very important when you're thinking about signals to have some ideas in mind. So here are a few just quick examples. Here is the price of Google share price daily for about 5 months. So that's roughly a daily share price. That's about 150 days. So here, we see this time axis along the horizontal axis here, our 150 days. And then the vertical height is the share price at the close of that particular day. So that's a financial time signal. Another example here is the temperature at the Houston Intercontinental Airport in degrees Celsius over 365 days now, and each vertical bar here, again, is the temperature at a particular time during that day. So this is a temperature signal. And at the bottom here is an audio signal. The spoken words in a recording of the play Hamlet. And here, each of these heights at a particular time corresponds to the pressure fluctuations in the air that's carrying the speech signal. So these are some simple examples that you can keep in the back of your mind as some examples of signals. Very important that you learn how to plot signals correctly. And particularly when you get into Matlab, it's important to remember that in a discrete time signal, the independent variable n is an integer. It is discrete, and therefore, if you're plotting signals like this in Matlab, it's important to use a command like stem that produces a plot where the signal is truly denoted as discrete time. What I mean by that is between the time 0.5 and 0.6, the signal has no value. The signal is undefined for these times in between 5 and 6. It is incorrect, and wrong, to use the plot command because basically, what this plot command does is through a linear interpolation, it basically does an inference of what actually happens between two integer time points, which is not necessarily correct. So if you're plotting in Matlab, you should use stem and not the plot command. Everything we've talked about up to now have been real signals. But we'll also have a lot of reason to deal with complex signals. And complex signals are signals where the dependent variable, x of n, takes not a real value, but a complex value. And let's just take a step back and do a very quick review and recall that if I have a complex number z that comes from the complex numbers, it can be represented either in polar form as z equals the magnitude of z times e to the j angle of z, phase angle. Or in rectangular form, a equals the real part of z plus j times the imaginary part of z. And here, you can see that we're using the engineering notation of j for the square root of -1 instead of the mathematician notation of I for the square root of -1. And so if we think of the dependent variable x of n being a complex number, that means that if we're going to plot a complex signal, we can plot it one of two ways. Either as our complex signal is comprised of a real signal plus j times the imaginary signal where the complex number x of n at time n is just decomposing into its real part at time n plus its imaginary part at time n. Or we can represent our signal as a magnitude signal multiplied by e to the j, a phase angle signal. Let's just look at some quick examples of this. Here's plotting a complex signal in its rectangular form. And we see that it consists of two plots. The first plot is the real part of the complex signal, and it's a discrete time signal. And the second plot is the imaginary part of that discrete time signal. And again, it's just a discrete time signal. So that's the rectangular form. We can also plot a signal in polar form. Here, we see the magnitude signal. Importantly, it is always positive. It always takes positive values greater than 0. And then the phase angle signal that generally can always be represented as taking a value between either -pi and +pi or 0 and 2pi. So the magnitude signal and the phase signal. So we're going to have a lot of use for polar and rectangular representations of complex signals. So just to summarize, the discrete time signals, x of n. Their independent variable is the integer n, and we're going to refer to n as the time variable. And the dependent variable x of n is going to be either a real or a complex number. And just remember to plot signals correctly in Matlab using the stem command. That's the right way to do it, and not the plot command, which is the wrong way to do it. Hopefully, you have enjoyed the presentation, and has contributed to or refreshed your knowledge. The objectives are to study less but smart, stay safe. Please like, subscribe and share with friends and colleagues.